Welcome to The Explainer. Today, we're diving into a medical paradox that seems to break all the rules. How can a 20 milligram dose of a drug actually be more powerful than a 40 milligram dose? It's a fascinating story about molecular precision, and trust me, it's going to change how you think about medicine.
So this is the big question we're tackling today, and it all centers on a really common acid reflux medication called pantoprazole. I mean, on the surface, it makes zero sense, right? But the answer isn't about the amount of the drug, it's actually hidden in the very shape of the molecules themselves.
You see, the key to solving this whole thing is realizing that a standard pantoprazole pill isn't just one single substance. It's actually a mix of two different molecules, and the secret lies in a really cool chemical property, molecular handedness.
Now, this property is called chirality, which is a bit of a fancy word for a really simple idea. Just think about your hands. They're perfect mirror images of each other, right? But you can't lay your left hand perfectly on top of your right. Well, some molecules are exactly the same way.
So a chiral molecule like pantoprazole exists as two of these mirror image versions. In chemistry, we call them enantiomers. For pantoprazole, one is labeled S, you can think of it as the left-handed version, and the other is R, the right-handed one. And here's the kicker. A standard prescription isn't a pure substance. It's what chemists call a racemic mixture, which is just a perfect 50-50 split of both the left-handed and the right-handed molecules. This is so important. That 40 milligram pill isn't 40 milligrams of the best ingredient. Nope, it's 20 milligrams of the S molecule and 20 milligrams of the R molecule. And as we're about to find out, they are definitely not created equal. So here's the deal. Even though they look like mirror images, our bodies don't treat them the same way at all. It's kind of like trying to shake someone's right hand with your left. It just feels awkward and isn't as efficient. Well, it turns out one of these molecules is the real star player.
And this is a core strategy in modern drug design. I mean, why would you give a patient a random mix when you know one version does all the heavy lifting? By isolating just the one superior isomer, you can create a drug that's not just stronger, but also way more predictable in how it works.
This table breaks down exactly why the S isomer is the superstar. First, it has less first-pass metabolism. Think of that as like a tax your liver takes on the drug. Less tax means more of the drug gets into your bloodstream. That leads to the second point, higher systemic bioavailability. More of the active ingredient is available to do its job. And finally, it's less dependent on a tricky enzyme, CYP2C19, which can vary a lot from person to person. This makes the drug's effect much more consistent and reliable for everybody.
And what's the result of all that better processing? Pure power. When they tested it, the S isomer all by itself was up to 1.9 times more potent than the 50-50 mix. That's almost twice as effective at doing its job.
Okay, so the theory is really solid, but does it actually hold up in real patients? Because that's the ultimate test, right? Let's take a look at the clinical data.
For an acid reflux drug like this, the measure of success is actually pretty simple. How long can it keep the stomach from getting too acidic? The big goal is to keep the pH level above 4.0 for as much of the day as possible.
And here it is, the solution to our paradox, laid out in a 2020 study. That first bar shows the standard 40 milligram mixed dose. It keeps stomach acid down about 42% of the time. Now look at that middle bar. That's just 20 milligrams, half the dose, but it's the pure S isomer, and it performs better, working for over 45% of the time. There you have it. Less drug, superior result. It's incredible.
And just like that, the mystery is solved. It was never about the total dosage. It was about purity and precision. By getting rid of that less effective right-handed molecule, a smaller, smarter dose can get you better acid control.
So what's the big lesson here? Why does this kind of molecular detail actually matter for patients and for the future of medicine?
Well, for patients, this isn't just some interesting science fact. This level of precision means you get faster acid suppression and a much more consistent, reliable result. You're getting better effects with a smaller dose, which puts less of a metabolic strain on your body. It's just smarter medicine, plain and simple.
And you know, this isn't just a one-off story about one drug. This whole process of taking an old mixed drug and isolating the better half has a name. It's called a racemic switch, and it's a major trend in pharmacology, a really powerful way to improve medications we've been using for years.
The pantoprazole paradox shows us that digging deeper into how molecules work can lead to way better treatments. As our tools and our knowledge get even more sophisticated, it leaves us with a final question to think about.
Just how much more precise can our medicine become?